Have you ever really stopped to think about magnetism? It's this incredible force that's completely invisible, but it's absolutely everywhere. It's truly universal. From the tiniest little atoms to the biggest galaxies, our entire universe is just woven together with these magnetic fields. It's a fundamental force that literally shapes our world, and by the end of this, you're going to see exactly how. So let's kick things off with a question you've probably had since you were a kid playing with fridge magnets. Why does a magnet snap right onto the fridge door, but if you try to stick it to an aluminum can, nothing happens? It completely ignores it. Why are some things so strongly attracted and others not at all? Well, that's the big mystery we're going to solve together right now. Okay, so before we can answer our big question, we've got to get on the same page. We need to understand the basic rules of the game, the fundamental properties that define every single magnet out there.
So every magnet, no matter how big or small, follows 4 simple rules. First, they all have 2 ends, a north pole and a south pole. Second, you know this one, opposites attract and likes repel. North and south pole together, but 2 north poles will push each other away. Now, rule number 3 is super important. You can't have one without the other. You can never, ever find a north pole all by itself. This isn't like electricity with its separate positive and negative charges. Poles always come in pairs. And that leads directly to rule 4. If you take a magnet and snap it in half, you don't get a separate north and south piece. Nope. You just get 2 new, smaller magnets, and each one has its own north and south pole.
So if this magnetic force is all around the magnet, but it's totally invisible, how in the world are we supposed to see it? Well, it turns out there's a really cool and kind of beautiful way to do just that. And here it is. This is how you make the invisible visible. If you sprinkle tiny iron filings around a magnet, you can literally see its field of influence take shape. Each little piece of iron basically acts like a tiny compass needle, and it lines itself up perfectly with the magnetic force. What you get isn't just a random pile of dust. It's this beautiful, ordered pattern that gives us a perfect map of the magnetic field. And this map, these field lines, tells us a few key things. First, they always form these continuous, closed loops. They flow out of the North Pole, loop around to the South Pole, and then go right back through the magnet itself. They don't just stop in the middle of nowhere. Second, they never, ever cross each other. And finally, you see how the lines get all bunched up and crowded near the poles? That's not an accident. The closer the lines are together, the stronger the magnetic force is in that spot. Okay, so now we're ready to get to the heart of our original question. To really understand why some materials are magnetic and others aren't, we can sort them into 3 groups. It's actually helpful to think of them as having 3 different personalities when they meet a magnetic field. First up, we have the diamagnetic materials. You can think of these as the reclusives, the introverts of the material world. When you bring a strong magnet near them, they're actually weakly repelled. They get pushed away just a little bit. It's a very subtle effect, but it happens in things like copper and even water. They just want to be left alone. Next, we've got the paramagnetic materials. These are the casually interested observers. You bring a magnet near and they're weakly attracted. Think of aluminum or oxygen. Their atoms act like tiny, disorganized compass needles. A magnetic field can get them to kind of pay attention and line up a little bit, which creates that weak pull. But as soon as you take the magnet away, poof, they go right back to being a random mess. And finally, we have the ones you've been waiting for, the superfans, the ferromagnetic materials. These are the rock stars, like iron, nickel, and cobalt. They're not just weakly attracted, they're powerfully attracted. And what's more, they have this amazing ability to become permanent magnets themselves. They don't just show casual interest, they join the fan club and become magnets in their own right. So this table really lays it all out. Diamagnetic materials get pushed away. Paramagnetic and ferromagnetic get pulled in, but the real difference is strength. Paramagnetic is a weak attraction, while ferromagnetic is super strong. And here's the most important part. Look at that last row. Can it become a magnet? For diamagnetic and paramagnetic, the answer is no. But for ferromagnetic materials, it's a resounding yes. That ability to hold on to magnetism is what changes everything. So what's the big secret? What is it about these ferromagnetic materials that gives them this magnetic superpower? Well, to find out, we need to zoom way, way in and look at what's going on inside. The secret ingredient is something called domains. You can think of them as tiny pre-magnetized neighborhoods inside the material. Within each of these little domains, all the individual atomic magnets are already working together, all pointing in the same direction. So each domain is already a tiny, powerful magnet all on its own.
So, in an ordinary piece of iron, all these powerful little domains are just jumbled up. They're pointing in every possible random direction, so their magnetic effects all cancel each other out. But the moment an external magnetic field comes along, it's like a drill sergeant barking orders. It forces all those random domains to snap to attention and align. And suddenly, all their individual strengths add up, creating one large, powerful magnet. And in something like a fridge magnet, they stay that way even after the drill sergeant is gone.
Okay, so this is all really fascinating science, I get it, but why does it matter? How does knowing about these different magnetic personalities actually impact our daily lives? Well, the short answer is, it's the engine of our entire modern world. That relationship between magnetism and electricity, it powers every single electric motor and generator. The ability to flip the alignment of those magnetic domains is literally how we store data on computer hard drives. The incredibly powerful magnets in MRI machines let doctors see inside the human body without ever making a cut. And magnetism is what allows high-speed maglev trains to literally float above the tracks. Almost all the technology that defines our era relies on these principles. So let's end on one final thought. We've established pretty clearly that magnetic monopoles, those lonely, isolated north or south poles, just don't seem to exist in our universe. So what then is the simplest, most fundamental magnetic element? The answer is the dipole, a tiny inseparable pair of a north and a south pole. It's the ultimate building block for everything we've talked about today, from the spin of a single electron all the way up to the massive magnetic field of the Earth itself. Thanks for joining me.